Okay, maybe I start now. So the topic of my talk is essential dimension. Okay. Well, the notion of essential dimension was introduced by two people, Buhler and Reichstein, in a paper in 1997. In a special case of a finite group, then they defined essential dimension for algebraic groups, and later a more general definition were given for quite wide algebraic variety of algebraic objects. So essentially what's happening is that for algebraic structure, whatever that means, we assign a number. Integer, non-negative, which is called the essential dimension of the structure. And this number measures, in some sense, the complexity of the structure. And the main property of this number is that if you have a surjection, structure B surjects on structure A, then the essential dimension of B is greater or equal to the essential dimension of A. Well, one of the possible applications of essential dimension is as follows. When you want to classify objects of certain type, suppose we want to classify objects of type A. So you make a list of possible objects in A, L, and the classification statement is a map from the list to A, and this is surjective if this classification is correct. So in particular, we have the inequality. Essential dimension of L is greater or equal to the essential dimension of A. But the classification statement could be very complicated, and just at the very beginning, maybe it makes sense to compute these numbers, and very often this is possible. If this inequality doesn't hold, then of course the conjecture fails. So just the first step of doing a classification thing is to compute the essential dimensions of those structures. Well, I would like to start with the definition of the essential dimension. It is very, very general and a bit boring. So first of all, we fix a ground field F. And we consider structures which admit the base change operation. In other words, we consider a functor A from the category of field extensions of F. So objects are arbitrary field extensions of F with homomorphisms over F, just to the category of sets. So we take any field K to the set A of K, and this is viewed as a set of algebraic structures. Over K. And if you have a field extension, then you have a map making the base change. Okay, let's take any field extension K over F and any algebraic structure. So it's an element of the set A of K. And suppose we have an intermediate field between K and F, the field K0. So we say that A is defined over this intermediate field K0 if A belongs to the image of the map from A of K0 to A of K. So it comes from some element which may not be unique over K0. And then the essential dimension of that element A is the minimum of over all fields K0, so that A is defined over K0 of the transcendence degree of K0 over F. So we measure the complexity of the field by the transcendence degree of that field. And then the essential dimension of the whole structure is the maximum of the essential dimension of A over all field extensions and all elements in the set A of K. So this is the formal definition of the essential dimension of the structure. So let me give you a couple of examples. When you can compute the essential dimension just directly from the definition. Let's take an algebraic variety over F. There is an associated functor, set of points. X of K is a set of points of X over K. So we can view X as a functor, and then it follows immediately from the definition that the essential dimension of X is just nothing but dimension of X. Well, the second example shows how to approach the calculation of essential dimension in general. So you fix an integer n, and the functor takes a field K to the set of similarity classes of n by n matrices over K. Mn of K modulo the conjugation. So what's the essential dimension of that functor? So if you delete this conjugation, factorization, then of course it will be n squared, because this is a set of points of n squared dimensional variety. But in general, for this functor, the rational canonical form shows that every matrix is a block diagonal matrix with the companion matrices at the diagonal of that form, so 1 below the diagonal, and 0 everywhere but in the last column. The last column has exactly as many elements as the size of the matrix, and we see that this matrix is defined over a field generated by the entries of the last column. So the essential dimension of that matrix is at most the size of the matrix. So we see that the essential dimension of this functor is at most the number n. On the other hand, we have a map from A to the affine space of dimension n over the ground field, which takes a matrix to the coefficients of the characteristic polynomial. And clearly this map is surjective. So the essential dimension of A is at least the essential dimension of the affine space, which is just dimension of the affine space is equal to n. So we got the value n for the essential dimension. So this is very typical when you calculate the essential dimension. You try to find an upper bound, you try to find the lower bound, and if you are lucky, those bounds match, and then you get the precise value of the essential dimension. This is the general strategy. Okay, so the first class of interesting functors arises from torsors over algebraic groups. So the essential dimension of algebraic groups. Well, G is an algebraic group over field F. And for the functor, you take the following. G torsors applied to K is the set of isomorphism classes of G torsors over K. So in other words, another name for the G torsor is a principal homogeneous space. So G acts simply transitively on such principal homogeneous spaces. So by definition, essential dimension of G is the essential dimension of that functor. So this number measures the complexity of G torsors of G. Well, there is a big source of interesting groups and G torsors. Suppose you have an algebraic object, whatever that means. It could be an algebra with involution, quadratic form, even a variety. So let's take a algebraic object. And we require the structure of a base change. Another object B is called a twisted form of A if A and B are isomorphic over some field extension. A over K is isomorphic to B over K for some K over F. Now let's take the automorphism group of the object A. So very often this has a structure of an algebraic group. And then if you take a twisted form of A, sorry?
In what sense?
In the sense that there is an algebraic group that the set of points of G over any field extension K is equal to the automorphism group of A lifted to K. Okay?
So you use Z as an algebraic group.
Yeah, so there exists an algebraic group G such that G of K is equal to A automorphism group of A over K. So if you take a twisted form of A, then E, the set of isomorphisms between B and A also can be viewed as an algebra is a variety. Very often, again, there is a variety E such that the set of points of E over any K is the set of isomorphisms between B over K and A over K. And this is exactly a G torsor over K. Because any two isomorphisms between B and A differ by a unique automorphism of A. So we get a map between the isomorphism classes of twisted forms of A and G torsors well, actually this is torsor over F. Okay, G torsors over F. So we got a map. And very often this map is a bijection. Let me give examples of that. Well, algebra of matrices over F. The automorphism group is the group of points of PJLN. Therefore, the twisted forms of the group of matrices are in one-to-one correspondence with the torsors for PJLN. So those are central simple algebras of degree n, of dimension n square over F. In one-to-one correspondence with PJLN torsors. So the essential dimension of PJLN then measures the complexity of the class of central simple algebras of degree n. But also PJLN is the automorphism group of the projective space, Pn minus 1. And the twisted forms of Pn minus 1 are called Severi-Brouwer varieties of dimension n minus 1. So PJLN torsors at the same time correspond to the Severi-Brouwer varieties. Of dimension n minus 1. Well, if you take the orthogonal group of a non-degenerate quadratic form of dimension n, then the twisted forms of a quadratic form of dimension n is also a quadratic form of dimension n, non-degenerate. So the G torsors are in one-to-one correspondence with non-degenerate quadratic forms of dimension n. We take the symmetric group as n, and this is the automorphism group of the algebra f to the n, the product of n copies of the algebra f. So the Sn torsors are in one-to-one correspondence with the twisted forms of Fn, and those are Étale algebras of degree n. Étale F algebras of dimension n. And you can continue this list of many interesting algebraic objects, like algebras, quadratic forms, algebras with involutions, and so on, are at the same time can be viewed are G torsors for various algebraic groups G. So how to compute the essential dimension of an algebraic group? Again, we have two strategies to do the upper bound and lower bound. For the lower bound, one can use the homological invariance of algebraic groups. So if we have a functor, well, now we have an algebraic group, G, And suppose we also have a Galois module over F. So a continuous module with the action of the absolute Galois group of F. And a cohomological invariant is a morphism of functors from G torsors over field extension K to Galois cohomology of certain degree D of K with values in M. And one can define the notion of a non-trivial cohomological invariant, which should be non-trivial, so such map should be non-trivial for certain field K. In fact, containing an algebraically closed subfield. And then there is a theorem, well, actually it's theorem of Serre, that if G admits a non-trivial cohomological invariant of degree D, then the essential dimension of G is at least D. That is because if capital K is a field extension of transcendence degree less than D, then the group vanishes if the base field is algebraically closed. Well, example. Let's look at the ON torsors, so quadratic forms of degree n to the same as ON torsors. So every quadratic form over a field characteristic different from 2 is diagonalizable. So it's a sum of squares with the coefficients. Immediately from here we see that every form is defined over a field generated by the coefficients, so the essential dimension of this functor is at most n. But on the other hand, there is an non-trivial invariant of quadratic form of degree n, the Stiefel-Whitney class of degree n. You take the cup product of A1, A2, An. Every symbol A for an element in the field can be viewed as an element of H1, K, Z mod to Z. So the cup product is inside Hn, K, Z mod to Z. And this is non-trivial. So we get the other inequality. So the essential dimension of the class of non-degenerate quadratic forms of dimension n is exactly equal to n. What about the other bounds, the upper bounds? Well, let V be a generically free G representation. Generically free means that the stabilizer of the generic vector is trivial. Then there is an open G equivalent subset, non-empty, which admits G torsor to some variety, I'll call it X. And in fact, every torsor over field K So you take at least infinite field extension, infinite field K, which is an extension of F. Then every torsor E over K, it's a G torsor, comes from that torsor by the pullback with respect to a point of X. So there is a point of X, and which can be completed to a diagram like that, which means simply that the functor from the points of X maps surjectively to the functor G torsors. And this follows that the essential dimension of G is at most the dimension of X, which is dimension of the vector space minus dimension of G. And so this is an upper bound for the essential dimension of G. Very rarely the bound for upper bound like this matches with a lower bound given by homological invariance, and so we get precise value of the essential dimension of G. Well, there is a special case of the essential dimension called the canonical dimension. So we take a functor A from fields over F to sets, and then we collapse this functor in the following sense. We define the other functor A hat from fields to sets, defined as follows. It's empty if A of K is empty, and it is just one point set. Well, you can write whatever you want, just one point set otherwise. So we collapse possibly a very big set to just one point. And we call the canonical dimension of A just essential dimension of that functor. Well, it looks quite artificial, but it's another number measuring something about the functor A. And by the way, it depends only on the class of fields, field extensions for which A of K is non-empty. So essentially, it's a measure of the class of field extension, closed under extensions. So the interesting example is when A is given by a variety X. You can rewrite the definition, unfold the definition, and see what this means for a variety X, at least in the case when X is regular and complete. So the canonical dimension of X is the following. You look at all possible rational maps from X to itself, and then compute dimension of the image of this map. And then take the minimum. So there is a connection to birational algebraic geometry in this sense. Of course, if X has a point, then this canonical dimension is 0 because you can map everything to that point. But for some varieties, this could be a non-zero number. Of course, it's at most the dimension of X. Minimum dimension. Maximum is for the identity the whole. Sorry? Well, if this is equality, X is called incompressible. X incompressible if the canonical dimension is equal to the dimension. So in other words, every rational morphism from X to itself is dominant. Well, example. Actually, it's due to Karpenko. Let's take this very broad variety of the algebra A. And then you ask whether it's incompressible. The answer is that it is incompressible if and only if A is a division algebra and the degree of the algebra is the power of a prime. You can prove this using algebraic cycles. The idea is that any rational morphism from X to itself gives you a cycle, the closure of the graph, in the Chow group of D is the dimension of the variety of X cross X. Now you can project it using the first projection to Chow D of X, which is just the Z generated by the class of X. And if you have a cycle alpha, the corresponding number is called the multiplicity of alpha. So the multiplicity of the graph is equal to 1 because it comes from a morphism. But the multiplicity of the transpose of this graph, when you interchange the copies of X, is exactly the dimension of the image of F. So Karpenko proves that for every cycle alpha, the multiplicity of alpha is always congruent to the multiplicity of alpha transpose under the conditions that it's a power of a prime p, and A is a division algebra modulo that prime p. And therefore, if the first number is 1 for the graph, then the second number cannot be 0. So this is well, at least a non-zero. Okay. I would like to come back to the essential dimension, and its essential dimension of finite groups. So let's take a finite group G. So what is a G torsor? G torsor over K is the same as the Galois G algebra over K. in particular, it could be a Galois field extension over K. So the essential dimension of a finite group just measures the complexity of the class of extensions with Galois group G. And generically free representation are the same as simply a faithful representation. So we have the obvious upper bound. The essential dimension of G is at most the dimension of every faithful representation. And the question is whether it's equal to the minimum dimension of faithful representation. The answer is no, and there are two examples. Easy examples. Essential dimension of the symmetric group S3 is a complexity of all degree 3 equations, but every degree 3 extension can be given by the following polynomial t cubed plus at plus a. Of course, you can skip the t square coefficient and you can equalize these two. So you just need one parameter to give degree 3 extension. So the essential dimension of S3 is 1. But there is no one-dimensional faithful representation for S3. And the other example is just takes the cyclic group of order 3. It's also 1. And if there are no roots of unity in the field, there is no one-dimensional faithful representation of C3. But in general, we have the following theorem. Karpenko, myself. Now, let G be a P group. And suppose that roots of unity of degree P, primitive root of unity of degree P, is in the ground field F. In particular, P is not characteristic of F. Then the essential dimension of G is equal to the minimum of dimensions of all faithful G representations. Well, as I said, that inequality is clear. How to prove the opposite one? This is the idea. You take the circle of G, the maximum elementary P group, which is in the center of G. And H is a factor group, mod C. And you start with E, an H tensor now. And consider the following gadget E mod G. You somehow over factor the E. And this is an algebraic stack. It's in fact a gerb bounded by C. And it classifies the points of this stack are the liftings of this tensor E to a G tensor. So E mod G of K, just the liftings, if any, could be empty, of course, of E over K to a G tensor. Oh, let me write curly X for this gerb. So we just need to get a lower bound for the essential dimension. So we start to write the inequalities. The essential dimension of G is at least the essential dimension of this curly X. Well, basically, we are interested in all the torsors, and curly X is responsible only for the liftings of some special torsor. And then, in general, there is no very nice connection between the essential dimension and the canonical dimension, but for the gerbs bounded by a very simple group, by the way, that is Z mod and PZ to some power S. We assume the roots of unity in the field, so that is C. There is the following relation between the essential dimension and the canonical dimension of X plus S. And you use valuation theory to prove this equality. Now, the canonical dimension of X depends only on the class of fields for which the set of points is not empty. Well, the gerbs are in one-to-one correspondence up to isomorphism to H2, whatever field, C. Well, let's say K, C, which is the sum of S copies of the P part of the Brauer group of K. So a gerb is given by a bunch of elements in the Brauer group of K. So these elements are trivial if and only if the gerb has a point over a field. So we get a bunch of central simple algebras associated to this gerb. And I would like to call them A high. And high, in fact, belongs to the basis of the group dual to C. And let's also take the corresponding Sverre-Brauer variety for the corresponding algebra A high. So the gerb has a point if and only if all Sverre-Brauer varieties have a point. So we have the canonical dimension of the product of those Sverre-Brauer varieties plus S. Now we would like to come back to the essential dimension. We would like to erase this letter C here and to know when this is incompressible. Of course, it depends on the choice of algebras, and different varieties have different dimensions, but the smallest one, the one with smallest dimension, is incompressible. This is proved using algebraic theory and algebraic cycles. So for certain choice of bases, you can write it's equal to dimension of the product of those Sverre-Brauer varieties plus S. Well, dimensions are degree of the algebra minus 1, dimension of the Sverre-Brauer variety plus 1, plus S. So just the sum of the degrees of the corresponding algebras. Well, this algebra can be trivial, especially if the very original torsor E is a trivial torsor. But now we make a special choice of E. We choose E generic. This is generic torsor. And we expect those degrees, well, actually the indices of algebras are the largest possible. They're always bound by dimension of representation. The index of the algebra is always at most a dimension of a representation V high. It's a representation of the group G, such that when you restrict this representation to the subgroup C, to the circle, it's given by multiplication by the character high. It's an upper bound. We need lower bound. But it turns out that for the generic choice of E, this is an equality for some very small representations V high. Using some computations with equivariant K theory, you see that it's equal to the sum of dimensions of V high for a certain choice of those representations. So this dimension of V, where V is the sum of V high. And then by construction, you see that the restriction of V on the circle is faithful. And then standard lemma shows that V itself is faithful. So that's how we construct the faithful representation for which you have this inequality, which is actually the equality. What is nice in the theory of essential dimension, that the definition of the essential dimension is very elementary, but the methods used in the proofs are from different parts of algebra. Next topic. Essential dimension of spinor and Clifford groups. Well, let me write simply Clifford group, even Clifford groups. So we have the orthogonal group ON. And we know that the essential dimension of n is equal to n because every form can be diagonalized. Well, similarly, you see that essential dimension of the special Clifford group is n minus 1. And the torsors for the special orthogonal group are quadratic forms with trivial discriminant. Now let me take, for simplicity, n even. And consider the Clifford group, gamma n. That's the even Clifford group, the one containing the spinor group. The torsors for the spinor groups and the Clifford group are very similar, and in fact the essential dimension of these two groups differ by at most one, but it's easier to consider the even Clifford group. The thing is that the gamma n plus torsors are quadratic forms Q of dimension n, trivial discriminant, and trivial Clifford invariant. In other words, the Clifford algebra vanishes for such a Q. And the last condition is very non-trivial, which makes the essential dimension of that group very interesting. So let me write down the table of values of essential dimension of this class of quadratic forms. Okay, this n is even, and here is the essential dimension of gamma n plus. Well, if forms like that have dimension at most 6, those are hyperbolic, and there is only one form. Essential dimension is 0. 8. Every form in this class of dimension A is a multiple of a Pfister form. So it's a form, a multiple of the tensor product of 3 binary forms. I write 1b for the form x squared plus by squared. So it's degree 8, dimension 8 form. It requires 8 parameters, 4 parameters, a, b, c, and d. And there is a non-trivial cohomological invariant, well defined, the cup product of A, B, C, and D. So you need just 4 parameters to get such a form.
What is ON plus? I missed the definition of ON plus.
Gamma n plus?
ON plus.
ON plus, the special orthogonal group.
SON.
SON. Well, I know if I can write S gamma n, but I try to find the uniform. 10. Well, another theorem in quadratic form theorem is saying that every form of dimension 10 with these properties is isotropic direct sum of a-dimensional form plus hyperbolic plane, so it's the same number 4. Well, for 12, that was computed by, well, classified by Pfister. Well, any form of dimension 12 is a scalar tensor product of a binary form, A, B, and so-called Albert form, xy minus xy minus u minus v uv. And then you count the number of variables, you get 6, right? 6. So that's Pfister. Well, forms of dimension 14 also classified, and that was done by Rost. And then using Rost classification, you see that the essential dimension is equal to 7 for this class of groups. And now starts something interesting, because we don't have classification of forms of higher dimension. But nevertheless, you can compute the precise value of the essential dimension of gamma n plus. And this value turns out to be exponential in n, which you cannot see from that table. So the thing is that after 14, the semi-spinor representation, which has dimension, well, some exponent of 2, becomes generically free. So you get upper bound given by the semi-spinor representation. And it's exponential. You have lower bound using a certain finite subgroup. Well, you have spin n mapping surjectively to the special orthogonal group. Here you have finite group of diagonal matrices, z mod 2z to the power of n minus 1. And then you take just the inverse image of that group, H. And the behavior of H is very different from the behavior of that group. This group has small faithful representations. And this group H has the minimal faithful representation is very large, of dimension, again, power of 2. And you can try to compare this upper and lower bound, and with some additional tricks, you get precise value. Oh, by the way, I should give people names of people who proved this. So that was done originally by Brosnan, Reichstein, Vistoli, in some cases, and finally it was completed by Chernousov and myself. So we know now the precise value of the essential dimension of gamma n plus for all n. The answer depends on n modulo 4, at least when n is 2 modulo 4. In this case, the answer is very simple. It is 2 to the power of n over 2 minus 1 minus n minus 1 over 2. So we just subtract the dimension of the spinor group, and it's the 2 power. So in particular, if you continue computation, for 16 the dimension is 23, and for 18 is 103. So it grows exponentially. It should mean something. So probably means that, well, there is no at least simple classification of forms of a dimension 16 and higher. Yes. And secondly, the classifying space of the Clifford group is quite complicated. So I mean the following. Let's take the classifying torsor I already mentioned, namely V generically free gamma n plus representation. Then you can choose an open set on empty with a torsor to X. So X is an approximation of the classifying space of the special Clifford group. And the fact that all the forms up to dimension 14 can be classified actually by independent parameters, algebraically independent parameters, means that this has very nice property. It's almost rational variety. In fact, it's the retract rational. Retract rational for n at most 14. And maybe the fact that things becoming more complicated after this border is related also to the fact that the classifying space of the Clifford, even Clifford group or Spitter group, is not retract rational for n starting from 16. But it's a wide open question. In fact, we don't have any example of a connected algebraic group, well, a split algebraic group for which the classifying space is not retract rational. But something interesting is happening after this border. And certainly we have two ways to measure the complexity of torsors. One is the essential dimension, and the other one is the property of the classifying space. There is no obvious relation between them, but there should be one. Maybe I will finish with one section on central simple algebra. It actually doesn't matter what base field is.
Even if you started with a field that contained the complexity of the result.
Yes, this computation is for over any field, in particular over complex numbers. Central simple algebras. So the essential dimension of the class of central simple algebras of degree n is the same as the essential dimension of PGLN. And very little is known about this number. Well, it's at most quadratic. You can prove that it's at most n squared minus 1, but even can improve this a little bit, but at most quadratic. But we don't have any reasonable lower bound at the time. Well, let me recall a wide open question in theory of central simple algebras. The question is, if n is prime, an algebra so has prime degree, is it true that A is cyclic? So it's a cyclic algebra is given by a cyclic extension L over base field and some element in the base field. In the case when the roots of unity of degree n are in the field, the cyclic extension also given by one parameter, k and root of b. So we need just the two parameters a and b to give a cyclic algebra. So if this answer to this conjecture is yes, and if there are roots of unity in the ground field, then we will get from the conjecture that the essential dimension of this class is equal to 2. And my dream is that one day someone will come with the proof that this essential dimension is greater than 2 for n at least 5. Because when n is 2 and 3, the answer is indeed yes to that conjecture. So that would be, of course, an impressive application of the essential dimension business. But it is in the future, I think. Okay, thank you.
Dans le tableau qui est là-haut, qu'est-ce que les invariants cohomologiques donnent? Je suppose qu'ils donnent beaucoup moins bien que les bornes que vous avez. Mais qu'est-ce qu'ils donnent, par exemple, pour 16, 18? Les invariants cohomologiques. Est-ce qu'il y en a?
We don't know any cohomological invariant of that group. Yeah, there are no invariants to show a lower bound. Well, there are some, but very simple ones. No.
So can you compute the cohomological invariance modulo 2, for instance?
Yeah, you can compute. So the invariants don't help to get any bound for that group. You mean the spinner group?
Oh, no, it's like to correct things.